Okay, so I kept talking about exotic smooth structures, so I will try to construct a few today. So that's the aim. And so the construction, there will be two constructions I would like to introduce. And the first one is called rational model. And this was invented by Stipsicz and Ron Stern, somewhere in the mid-90s. And so the idea is the following. So suppose, so yesterday we discussed if you have a four-manifold, we can blow it up. Or we can consider the inverse procedure if we have a four-manifold Z and we see a sphere in it. So Z is a four-manifold, this is S embedded sphere with QZS minus 1. So the set intersection of this surface is minus 1, meaning that you can push it off a little bit, and it will intersect in one point, and the point will have sine minus 1, by which I mean that we take an orientation of S, we sort of transpose it to this little push off. So at the intersection point, we have four vectors, two tangent to S, two tangent to the nearby guy. It doesn't matter which order you take, and it does not match with the orientation we fixed on the four-manifold. Then, by taking the tubular neighborhood, first we realize that the boundary of the tubular neighborhood will be S3, and what we can do is just cut it out and glue back at D4. So cut out and glue back D4. So by this way, we sort of erase this minus 1. This is what we call a blow down. So this is blow up, and this is blow down. You can interpret it in the way that we just erase this from the connected sum, or you construct in the holomorphic family, you construct a map, exactly my map from the earlier, from tau to C2, where one fiber of CP1 just connects to a point. Or you can imagine that you sort of pierce the balloon and it connects to a point. I leave it for you to imagine. And this is what we would like to generalize. And the generalization will involve other curves and further configurations, and it will be a little bit weaker. So this is, I will explain why it's called rational blowdown as opposed to just the regular blowdown. Okay, so here is the first example. So suppose that instead of having a sphere with set intersection minus 1, where the regular blowdown works, assume that Z, or good old four-manifold, contains a sphere S. So by which I always mean that it's a smooth submanifold and it is diffeomorph to S2 with self-intersection. And now, not minus 1, but minus 4. Okay, so the mental picture you should have is this is Z, there is this S, and the push-off intersects it in 4 points, all with the same sign, all with negative signs. Where do we see something similar to that? Well, consider the quadric curve C in CP2. So this is just twice the generator. It needs a little bit of a thinking that this holomorphic curve is a sphere again, and its self-intersection is 4. It's twice the generator, so if you square it, it's 4. So, I mean, you can imagine that you take two projective lines, and then you sort of perturb a little bit the equation, and then you get a connected, smooth submanifold in CP2, which is now a sphere of square 4. Okay, so now I will modify my picture, and I would like to sort of indicate that it's a smooth submanifold, something like that. And what my plan is to cut out the tubular neighborhood of this guy, just as before, and reglue something. And what we need is a four-manifold which has the same boundary, but with the opposite orientation, because we have to glue with orientation reversal diffeomorphism. So the boundary of this is a length space. We have to go through a little bit. It's an S1 bundle over, so this Y is the boundary. Y is the boundary of the neighborhood of S. And this is an S1 fibration of over S2 with Euler number -4. So what we need is a fibration, an S1 fibration over the sphere with Euler number +4. Luckily, this is exactly what we have here. So we just cut out the tubular neighborhood and glue in. So you just take this portion, the complement, you just take, I don't know, W is CP2 minus the tubular neighborhood of C, and then we just glue it in instead of that. So cut out and glue in. I might, yeah, okay, this is what we do. That's great. We get a new manifold, which I will denote by Z S. So doing so what happened? We did have an essential homology class. It's non-zero in homology because it intersects itself non-trivially, and we substituted something else. What is it? Well, this is not the disk. In the previous example, we substituted the disk, but unfortunately, this is one and only boundary. It's S3, so we cannot do that. Well, this is a four-manifold. So this W is a four-manifold with a simple rational model. Needless to say, D4 has a very simple integer homology, and the claim is that H lower star W with rational coefficient is the same as the disk with rational coefficient. You can check that by taking, say, the Mayer-Diacon sequence. The rational homology of the boundary of the neighborhood is 0. It has finite fundamental group, everything disappears. And so this yellow thing has this property as the single generator of H lower star or H2 of CP2 is in the neighborhood of C, which we remove. There is nothing left. These gadgets, those four-manifolds with boundary, which satisfy these conditions, we call them QHDs or rational homology disks. So W is that QHD4 and rational homology disk. So this sort of explains the name of rational blowdown. In the usual blowdown, we take out something and replace it with a disk. In the rational blowdown procedure, we take out something and we replace it with a rational homology disk. It's not exactly a disk, but as far as homology goes, it's exactly the same. Okay, so this is the idea. And then we would like to see some cases when it is useful And of course, we have to pay attention to two things. We would like to follow what happens with the topology. So are there signature parity, so we can use Freedman's theorem. And more importantly, we also would like to understand what happens with the Seiberg-Witten invariants. So it really produces some new smooth structure. And this is exactly what we will do. I will be very, very sketchy, if so, with the Seiberg-Witten computation. I will give you a vague idea, but not the deeper document. Okay, so, but we would like to find the right candidate for C and the right candidate for the minus 4 spheres. So we go back to our earlier examples. So recall there is this vibration CP2 sine times CP2 bar to CP1 elliptic vibration containing singular fibers. This is what we went through yesterday, and we would like to pick specific singular fibers. So is the vibration, of course, the vibration depended on our initial choice. You remember we had to pick a curve C0 and a curve C1, and then blow up, and then we got the vibration. So then assume that the vibration contains fiber which is like a nodal curve, like a nodal cubic curve. So let me just explain what the nodal cubic curve is. So first of all, we take CP2, and a cubic curve is cut out by a homogeneous cubic equation, and we take the following. So this will be a curve which will look like, so I have these schematics which indicates that it's a sphere with 2 points identified. You can imagine it in two different ways. Either you say that we start with a regular elliptic curve, a torus, and then because of some degeneration, one curve suddenly starts to shrink, and then at the end of the day, it just shrinks completely to a point. That's one way to see it. Or you can think that it's a sphere mapped into CP2 by 2 points identified. If you think a little bit, the two pictures are exactly the same. My usual picture for the degeneration is something like this. But I don't know how useful it is. So it's a very unfortunate donut. Right, something happens. Okay, so this is one of my cubic curves, and I pick the other one to intersect it in 9 points away from the singularity. I will not give you the specific equation, but you can come up with another one where it intersects in 9 points away from the singularity. So when you blow up, then at the end of the day, you will see a fiber which will look exactly like that. Why did I say that which is like a nodal curve? Well, topologically, it's exactly like a nodal curve, except the tubular neighborhood changes because here the homology class has set intersection 9, but when you blow up 9 times, it will have set intersection 0. The fiber doesn't change, but the surrounding space does change, of course, because we blow up like in now different points. Okay, so we can assume that this vibration have that.
Am I right that in this total space is not cubic in any sense because
which one?
Am I right that this fiber in the total space is not cubic in any sense?
I mean, it's a cubic in CP2.
Yes.
And then what do you mean by a cubic in?
Yeah.
Yeah, it's a fiber.
It's just,
yeah. We start with a cubic and then it loses its cubicness. Yeah, but it becomes a fiber. Okay, so and now we do something which is not completely necessary, but it eases the discussion. We take two of these copies and do the fiber sum which we discussed last time. So instead of having this fiber in E1, we've identified the E2. So upshot or consequence, a fibration E2 with a fiber of this type. Why do I do that? Because E1 has B2 plus equals to 1. And I already mentioned, and we will reach that point in Tom's lectures, when Seiberg-Witten theory becomes more complicated in the B2 plus equals 1 case. That's one reason. The second is that the statement I will state would not be true for E1, and that's even a stronger statement. Okay, so let's stick to that. So there is this fiber, there is this other one, and I will use only one of them. And then it comes with this fibration, C1. Okay, so this is my Z. No, not exactly. This is my Z1. So E1 with such a, we call it a fishtail. Probably you understand why. Okay, so this is our starting position, and now we apply a blow up. Let's blow up this point. So blow up the singular point of the fiber. It's a smooth point of the four-manifold, but a singular point of the embedded two-dimensional surface. And what we get, so let's call it F. There is F tilde and the exceptional divisor P inside Z1 blown up once, which will be my Z. And my claim that this will be a sphere of self-intersection minus 4. Okay, maybe we should step back a little bit and recall what this blow-up procedure was from yesterday, how a smooth topologist thinks about the blow-up. So here is my X. And I have two surfaces transversely intersecting one point, and this point is a positive intersection, by which I mean that I take a basis of this oriented surface, then the other one, concatenate, and it's exactly an oriented basis in that point of X. Okay? And I take CP2 bar, and I take two projective lines, but now the four-manifold orientation is reversed. So this intersection becomes negative. And now I take the connected sum as the blow-up procedure demands. What happens then? I take the connected sum exactly in these 2 points, which means I delete a little neighborhood of that point, a little E4, and likewise here. And I would like to match them in a way that the lines match up with the lines there. What is the boundary? The boundary is S3. The intersection of the two surfaces with the boundary is a Hopf link. We know what the Hopf link is, right? It's just this, and this is the positive Hopf link. This is reflected, so these are oriented circles. And now, of course, I have to. So how is that? This is oriented like that, so this is a positive Hopf link. Likewise, here, the boundary is S3, but now there is the negative Hopf. And when we glue them together, what happens is that this intersection and this intersection will somehow disappear. This surface will continue in this one, and this surface will continue in the other one, and we erase the double. Does that make sense? I mean, this is not algebra geometric description, but I think it's quite visual. And this explains what happens if we blow up the double point of the surface. I mean, at the blow up, we don't know whether the two branches come from the same surface or locally they are completely different. So what happens is that one of the exceptional divisors from CP2 will be joined with this branch of the intersection and the other one with the other one. So that explains that the originally F had self-intersection 0, But now in homology, it changed. F tilde is the good old F minus twice the exception divisor. And then you do the math, and it comes out to be, as a set intersection, will be -4. So we exactly have what we wanted for our picture. And then we just run the rational build-down procedure. So okay, apply rational build-down to E2 blown up once along F tilde -4 sphere. And we get, usually it's denoted by E2 sub 2. I will explain what the sub 2 means in this context. Okay, so this is a new four-manifold. So there are several claims I would like to make. So it is a theorem of Fintushel and Stern. Most of the steps are absolutely trivial, and I don't want to attribute it to them, but there is one, the last one, which is a little more complicated. So the first one is that pi 1 will be still trivial. You have to remember that E2, the original guy, was simply connected, and I claim that the new manifold will be also simply connected. And the reason is that there was a sphere in E1 intersecting this fiber in one point. Any of the blowups, any of the blowups will provide such a sphere that intersects at one. We can arrange this gluing, or we actually did arrange this gluing to match the spheres together. So the fiber in E2 will still have this dual sphere, the sphere intersecting at only one point, which survives for F tilde. So on the boundary, when we take out the tubular neighborhood, we are cutting along a length space, and the generator of the fundamental group will be contractible on one side. So the result will be simply connected. The other characteristic of E2 will be the same as E2. Well, this is not very hard to check, because what did we do? We blew up once. So we started with E2. We blew up once. This increases the Euler characteristic by 1. We substitute a point with a sphere. The point has Euler characteristic 1, the sphere has 2, so we increased by 1. But then we took out the -4 sphere, which has Euler characteristic 2, and replaced it with a homology disk, which has Euler characteristic 1. So nothing changed. Similarly, the signature doesn't change. This is again, by blowing up, we dropped the signature by 1, but I erased a negative self intersection guy, so I just corrected it back. Well, unfortunately, the parity changes, so well, that's not so great. Parity changes, but we will fix that in a moment. So unfortunately, the two manifolds are not homeomorphic to each other. One is spin, the other one is not spin. But let's live with that for a while. And the last thing is that the Seiberg-Witten invariants of E2 and E2 are different. So if they were homeomorphic, but they are not, then they would give us a nice exotic pair. I will try to argue for this a little bit later, and this is exactly why I attributed to fibrations. This is the hard stuff. But there might be a little bit of a question mark here. So we already ruined the homeomorphism type. So there is a sister theorem of that, when we are not taking E2, but we fiber sum more copies, so we can do this exactly the same for En, because all the operation I described now happens in this very little region. So we have the same, do the same for En, And now I will not write down the statement. So E and 2s have the same characteristic numbers, and the parity remains the same if n is odd. I mean, there are no other choices. The signature is minus 8n for n odd is not divisible by 16, so it cannot be spin. It can only be odd, so that's what it is. Okay, so once we delete this last statement, for every n odd, we see a pair of four-manifolds which are homeomorphic but not diffeomorphic. Okay. Of course, I promised something else. I promised in the last lecture that there are infinitely many manifolds which have infinitely many distinct smooth structures. Now we get infinitely many which have at least two. And so we will upgrade our rational homology story, rational low-level story. So notice that this procedure, the construction of W, can be extended. Sorry. Where is the stick? Yeah, anyway. Tom, what did you do? Oh, it's there. Okay, you didn't take it. Notice that
I think you put it anywhere.
the construction of W can be generalized as follows. So remember we have CP2 and the cube. Of course, there is a line, there is a projective line which intersects it in 2 points. Let's call it H. 2 positive points. And now I do a sort of annoying little trick. I reverse the orientation. Yeah. So now this is a -4 sphere. So set it as -4. It used to be 4, but now we reverse the orientation of the ambient manifold. This is a -1 sphere. Unfortunately, these intersection points become negative, right? Because we reverse the orientation of everything. But I can sort of remedy that by instead of taking H with the original orientation, now I flip the orientation of H again. So I hope you bear with me. I flip the orientation of the four-manifold, and I flip the orientation of one of these guys. So I end up with a configuration where we have 2 spheres, one of them with self intersection -4, the other one with self intersection -1, they intersect in 2 positive points. And now the fun begins. Now I blow up this point. So what happens? We will have a -5 sphere, a -1, and a -2. Right? The -h becomes a -2. There is the new exceptional divisor -1, and there is this old C, which now becomes a -5. And we are now in CP2 bar, connected some CP2 bar. And then I can repeat that. And actually, I have always a choice because I can blow up this side or that side. It doesn't matter.
Second, what you did?
I blew up this point. Okay. And so it was 2 curves in CP2 bar. Now I have 3 curves in CP2 bar connected some CP2 bar. There is a new -1 curve, this one. And these are the proper transforms of C and -H. So it's C tilde, and this is -H tilde, and this is the new. And then I can keep repeating that. But notice so this has the second rational homology is 2-dimensional. If I take out the tubular neighborhood of the -5 and the -2, then what's left over is the other. This is now W3. A four-manifold with boundary. The boundary is another length space. And this is also a rational homology. And then I can keep doing that. In fact, we can create a family of linear plumbing graphs. I mean, by which I mean that the sequence of spheres that they intersect each other according to the chain with some set intersections A1, A2 up to AN, a family G, and G is defined as the smallest family with two properties. The graph with a single -4 is in G, so that was my original guy. And if there is this plumbing A1, AN in G, then a new plumbing which starts with -2, A1, AN -1 is also in G. So this is sort of an inductive definition of a whole family of plumbings. This is exactly what you can construct with this construction. Of course, you take it like this or flip it around. This reflects whether I go at this point or that point. Does that make sense? It's a little complicated, but it gives you a family. Of course, there is a way better description of the family. These numbers can be organized in a continued fraction expression, and those are exactly the continued fractions of -p² over pq -1, p and q not -1, p equal to q, equal to 0. Okay, so this is a little bit of a number theory, and it's not very interesting. The interesting thing is that you can create a whole lot of plumbing graphs or sphere configurations for which the boundary of the tubular neighborhood bounds rational homologies. Indeed, let's call, I don't know, configuration P should be the simplest one, bunch of -2s, P of them, and -P-2. This is when I blow up the -5 to get the -6, and one more -2 on the other end, and then again I blow up the -6 to get the -7, and so on. I see some puzzled looks. Does that make sense? Okay.
Okay, quickly, what is the plumbing graph of this example?
It's like -5, -2. So the plumbing graph, the dot records a sphere with the self intersection, and the edge records whether they are connected, whether they intersect or not. So -5, -2. When I blow it up again, let's try to do it here. It used to be like this, -5, -1, -2. I blow up this point, so it will become, this curve will become -6, a new -1, this guy becomes a -2, and there is an old -2, and the plumbing graph is -6, -2, -2. And then, and I made a mistake, right? Like this. So for P equals 2, you get none of these, and you get a -4. For P equals 3, you get a -5 and a single -2, and so on. This is why it's a W3. Okay? And then we just keep doing that. So we get, now I will do another trick, not very nice, but you can upgrade this theorem for E. I'm sorry, I should finish first. So, yeah. So let's go back to this picture. In E2, we had this singular fiber. We blew it up once, so it became an embedded S2, and the exceptional divisor, this was my tilde, intersected it twice. So and this is -4, -1, and you see a very similar configuration than up there, so you can play the same game. You blow it up once, you get a -5, a new exceptional -1, and the old exceptional becomes a -2, and so on. So you find exactly that curve configuration, this one and that one, and all the P's in your several blow-up E2 or EN. And then you just take the tubular neighborhood of that configuration, take it out, replace it by the appropriate rational homology disk, and you get the new length. So you get, instead of En2, you get En_t. And the statement will be exactly that they are simply connected. So how should I write that? Maybe I will just write that. The chi, the other characteristic, this needs a little bit of a thinking of how many blow-ups you applied and how many curves did you erase by the rational blowdown. Their number will be equal, so the other characteristic doesn't change. The signature doesn't change. So this holds for every n at least 2 and every p, which is not a prime now, its p is at least 2. Right? So p has to be 2 because there are p minus 2 minus 2. Okay, and then finally there is this this parity. So the parity is odd if n is odd. There is no other choice because the signature is minus 8n as it states, so it's not divisible by 16. So the only choice is to have odd parity, and also odd if n even and p even. Yes, and even if n even and p odd. Okay. I mean, this is a statement, and I will not argue for that, but I know it looks like a stupid statement, but it is what it is. So if n is odd, you can see it. Okay. Okay. Let's spell it out. So parity odd if n is odd if n is even and p is even, and even if n is even and p is odd. Okay, so that's the statement. So and then the final line still applies. The Seiberg-Witten invariants of E and P are all distinct. So this is a vague statement. If you change n, then of course the homology, the rank of the homology is different. So of course they are different. If you fix an n, then you can imagine that they are living on the same second homology group and they are all distinct functions. Okay, so that shows that for these manifolds, this is an infinite collection of manifolds, and there are infinite many different smooth structures. I will get back to that statement at some point, but let me finish by giving you the second construction I wanted to talk about. And this is also due to Lefschetz terms. Not surgeries. So the input is something slightly different than it used to be. So suppose that X4 is a four-manifold containing a torus T. So there is an embedded torus in the four-manifold, a sphere S, so that the self-intersection of the torus is trivial, which just means that the tubular neighborhood of the torus is just T2 plus D2. So I will try to draw again. This is X. There is a torus with trivial neighborhood. The sphere intersects it once. Minus t, there is a unique transverse point. So this is part of the input. So there is a little geometric configuration plus a knot in elliptic. Okay, so these are the two inputs, and then we do the following. Consider the three manifold as 3 minus an open table neighborhood of the knot. This gives you a three manifold with T2 boundary. Well, we cannot do much with the three manifold in this four-dimensional setting, so we just promote it to a four manifold by multiplying it with S1. So this is a four manifold with boundary with three-dimensional force. Okay, so yeah, I don't want to draw. It's something like I don't know. And secretly there is this knot which sort of tries the whole story. And take x minus the open tubular neighborhood of t. Again, a four manifold with boundary T3, and glue the two to get xk, which is just x minus the tubular neighborhood, union of some phi, S3 minus uk plus S1. We have to be a little careful about how to choose this doing phi. So in order to get an oriented four manifold, we need the phi to be orientation reversing. And we also demand that the normal circle to T matches with the normal, with the longitude of K. The longitude of K lives on this closed boundary. Otherwise, we take whichever map we like. Okay, so this is not completely well defined. It does depend on phi in some cases, but that's okay. So we have a whole bunch of four manifolds, and here is a theorem. Again, the first part will be trivial. And I forgot. So if X is simply connected, then I1 of XK is trivial. This is the role of this dual sphere, that somehow the normal circle to the torus bounds the disk in the complement. The other characteristic of XK is the same as of X. This is not very hard to check because we take out from X, we take out something which has zero either characteristic, and we substitute with it something which also has zero either characteristic because it's a product of something with S1. Similarly, the additivity of the signature has that the signature remains the same, and here it needs a little bit of thinking that the parity stays the same. So we created a new four-manifold which is homeomorphic to X. So X and XK are homeomorphic. So that's great, and we hope that they are sort of distinct. And this is exactly what happens under some condition. The last part,
The complement will be simply connected.
say it again.
So you just require x simply connected or x minus t and simply.
So X is simply connected and S, collapses the, um, if X is symplectic, which for the present purposes only implies that has non-zero, not has non-trivial Seiberg-Witten invariants, then xk1 and xk2 are diffeomorphic would imply that the Alexander polynomials of the two knots are the same. Said differently, if you have two knots with distinct Alexander polynomials, then the two four-manifolds cannot be diffeomorphic. Somehow the Alexander polynomial is encoded in the Seiberg-Witten function. So this shows that if I can come up with an infinite collection of knots with distinct Alexander polynomial, and I have a symplectic four-manifold with this configuration inside, then on that particular topological four-manifold, I can create infinitely distinct smooth structure. So I don't need an example for Kn. It's just the twist knots. So we implement n full twists. Will do. And in fact, so these are my case, and X can be chosen to be En. Again, N should be at least 2 for the Seiberg-Witten invariants to be defined, and T is a fiber. And we have to check a little bit that there is this dual sphere, but this will be exactly a section of the fibration. So everything is fine. This tells us that there is an other infinite family of smooth structures on these guys. They are distinct from the one we produced earlier. And this leads us to a conjecture that if K1 and K2 are distinct knots, in the sense that K1 is not isotopic to K2, and K1 is not isotopic to the mirror of K2 either, even after mirroring, then the A and E and K1 and E and K2 are non-diffeomorphic. So the theorem is that once we fix one of the ENs, say the K3 surface, then the family of smooth structures on the K3 is at least as complicated as knot theory when you view it through the lens of the Alexander polynomial. And the conjecture is that it's as complicated essentially as knot theory, at least. And then there are a few more, which I constructed earlier. So this might give you an indication that we do not really have a good conjecture how four-manifolds look like. I mean, you know, what is there a structure very similar? You would expect something similar to like Thurston's conjecture, the geometrization conjecture, you know, that there is some order. And well, we don't know. Or maybe this is like dark matter, right? There's no idea. Okay, and before finishing, let me just give you one more example, which is a little bit more hands-on.
In the statement of the theorem, do you use the sphere other than I1?
No. So it doesn't have to be embedded, it can be merged, that's also good enough. And there are other versions to define to describe the situation, but I found it the easiest. But you don't. Still, it has to be there. Or something has to. Okay. And well, I will return to this question next time. But I would like to give you one more construction, which now will give us four manifolds with boundary. This example is due to Outbulut, and that has been found, I don't know, 35 years ago. Still works. Fantastic. So the four manifold, suppose K is an R with framing, i.e. with nearby node. So you have your knot in the free space, and this K prime goes around and a couple of times winds around K. We don't care how many times. This gives us a four manifold XK, which we construct in the following way. We take D4 with boundary S3, and here is the knot, K. Unfortunately, I am drawing it in a dimension reduced way, and I consider D4 union D2 cross D2, where glue down some phi, where phi identifies boundary of D2 cross D2. So this is my D4, this is my D2. And I take the boundary of the first D2 and the entire second one. So I will glue along these guys, mapping into S3, so that it is an embedding. And phi of in the middle. So when I take the circle across the origin, this will go to K. And when I take at 1, this should go to K prime. So this is how, this is, a detailed description of how to attach a four-dimensional two-handle to the ball. So I just attach this rectangle should be the same rectangle. These guys are here, and the middle goes to the knot, and the nearby knot is somewhere else. Okay, does that make sense? Okay, so we have a four manifold, XK, and here is my flame, or here is Huggin's flame. Whoops. So I will just draw two knots. The one will be a twist knot again. And the other one is a little trickier. And we introduce -4 twists here. This is my K1, that is K2. And K1 prime is a nearby knot, so that the linking number of K1 and K1 prime is -1. And similarly, K2 prime has the same property that they link exactly -1 times. Then the boundaries of xk1 is diffeomorphic to the boundary of xk2. So that needs to be checked. It's not very complicated, but this is where like Kirby moves and three-dimensional topology comes in. Using Freedman's extended theorem, xk1 and xk2 are homeomorphic. And finally, the two manifolds are not diffeomorphic. And very quickly, how can we see that? Well, it's a little bit longer story. What we have to notice is that this knot, K2, is a slice knot. Which just means that it lives on the boundary of D4, and it bounds an embedded disk in D4. You might see that by the following procedure. So imagine that we sort of cut this knot in here, and we do this. So this is now our original knot. It's just a two-component link. But if you are patient, you can see that this is actually a very simple two-component link. It's actually two knots sort of living very happily next to each other. You can just sort of push it inside and unhook and untwist these guys, and you get the two knots. So these guys definitely bound two disks inside D4. They actually bound two disks inside S3 as well. You can push it inside D4. So I will try to build up this sphere, and we are just here. No, we are here. We have two circles, two knots, and they bound two disks. And now I will just glue back this little band, so I can just attach the band, connect them, and you immediately see two disks connected by a band. That's a disk again, so it bounds a disk. Which means that after you glue this two handle, this disk can be completed into a sphere of set intersection -1, but it doesn't matter. What we can see is that the generator of the second homology in this guy can be represented by a sphere. And now the claim is that in XA1, this cannot happen. And I was thinking of telling you the idea of the proof, but I think it will just sort of complicate things. So let me just make the statement back. The generator of H2 XA2 Z can be represented by an embedded sphere. This is what we verified. And the generator of H2XA1 cannot. Next time I will give you a little argument for the second portion, and this verifies that the two four-manifolds cannot be diffeomorphic, since generator of second homology. I mean, we know what is this group. It's just isomorphic to Z. A generator of Z under a diffeomorphism should go to another generator of the other guy. So the genus function somehow distinguishes these two manifolds, and this is what I wanted to tell you today. So we are in the position of having very small exotic homeomorphic but not diffeomorphic manifolds, and in the closed case we have huge families all admitting infinitely many distinct structures. What I owe you is a little bit of an explanation of this one, and also how the Seiberg-Witten calculation can be done. So we'll do that tomorrow morning. Okay.